Good morning, Atamarie. My name's Stu Fraser, and I'm a forest pathologist and research group leader at Scion. Great. So today I'm going to be talking to you about epidemiology and control of red needle cast. So the overview of the talk. First, I'll give an introduction to red needle cast for those people who aren't so familiar with the disease, and just a recap for those who are. I'll then outline the research aims and approach that we've been taking. I'll talk about research we've been doing looking at the epidemiology of the disease. So this is all about understanding when, where, and why epidemics occur. I'll then go on to talk about some of the copper control trials we've been running, building on earlier work that demonstrated that copper had promise in controlled lab trials. So we've taken that further into field trials. And then I'll talk a bit about some work we've been doing looking at growth impacts of disease. And then I'll wrap up with some conclusions. So just as a bit of an introduction, red needle cast is a disease caused by two species of Phytophthora, which are fungal-like microorganisms. They're not fungi, but they act a little bit like fungi. Phytophthora pluvialis is the main cause of the disease, but sometimes we also get another species out called Phytophthora canovii. This disease was first discovered on the east coast of the North Island in 2008, but has likely been present in New Zealand for a longer period. This disease can cause significant growth loss after defoliation events. So in one study, it was found that 38% of growth was lost the year following a cast event. So this disease can have a significant impact on growth. So the aims of this work are to develop recommendations for cost-effective chemical treatment of red needle cast. The outcome being that industry can manage red needle cast in existing stands now and into the future. The benefit being increased productivity, at-risk stands are protected, and the industry retains its social license to operate. So the approach we've been taking is to undertake research to better understand the epidemiology of the disease. So that's the where, the why, and the when disease outbreaks occur. So we're doing research monitoring disease expression year on year to understand why we get outbreaks in certain years and not others. We're doing work within years, looking at when spores are released and when infection occurs within a year. That will give us a clue as to when it's best to apply treatments. And we're also undertaking controlled studies to parameterize an epidemiological model, which can kind of help us get into the black box that is red needle cast, understand the different processes better in the disease cycle to be able to predict when outbreaks may occur. The other area we've been working on is looking at copper as a potential control tool. So copper is used widely for control of Dophystroma, and previous work had shown that it showed promise in controlling red needle cast also in controlled lab and glasshouse trials. So we've taken that further into the field, so I'll talk more about those trials. And we've also been doing some work trying to understand the growth impacts of disease so as to enable a cost-benefit analysis. So I'm going to start off talking about the epidemiology of the disease, so the what, the where, the when, and the why disease epidemics occur. So the first thing to understand is that red needle cast is a very seasonal disease. So this graph shows monthly detections of Phytophthora pluvialis in our diagnostics lab over the last 12 years. And what you can clearly see is that we get peaks of disease in the middle of the year which is indicated by these red bars, which show the winter months. Conversely, in the summer months, which are indicated by these green bars, the free summer months, we get very few detections. So I'm just about to show a video of red needle cast expressing in a year, this year, over on the east coast of the North Island. So this video starts at the end of May this year and runs until August, the start of August, just before lockdown. And if you kind of concentrate on the fourth tree to the right, you'll see at the start of the video there's the red needle cast is also already expressing there. But as you'll see as this video runs, how quickly this disease progresses under the right conditions over winter. So as you can see, it started with a small amount of infection in one tree, and it quickly spread up the tree and to neighbouring trees, causing a large amount of cast by midwinter. But it's important to note that timing within a year can vary. So here we have a study looking at detection of inoculum at a site also in the east coast of the North Island over 3 years. And you'll see in the first year we had peaks in detection in autumn and spring, but in the second year we didn't get a peak until early summer, and then finally in the third year we got a peak in midwinter. And another really important thing to note is the repeated heavy outbreaks year on year are rare. So here in 2008, we have a stand that was really heavily affected, but then in 2009 is green and healthy. So work we're doing this year and under the Resilient Forests program is to develop a epidemiological model which will help us understand and predict when an epidemic of red needle cast may begin, peak and end based on forecasted weather, and to enable us to forecast whether a disease epidemic will occur in a certain year. So this model separates needles into susceptible, so that's the S on the left, and these are uninfected susceptible needles, and as the epidemic progresses they move to infected but still green needles, and then transition to infected red needles and then infected cast needles. And I'll just demonstrate this with some photos now. So you'll see in this photo there's a little bit of red infection in the middle, and then most of the needles around that infection are probably green and infected needles. As the disease progresses they change to infected and red needles, until finally they're infected and cast needles. So to help parameterize this model, this year we've been doing work looking at the impact of temperature on different life stages of the pathogen. So you'll see on the top 3 graphs we have 3 different time points after infection, and you'll see the top 3 are sporulation at different temperatures. The bottom 3 show symptomology development at different temperatures. And what you'll see is we had no spore production and no symptom development at 25 degrees. We had a very little amount at 5 degrees, but we had pretty much the same amount of sporulation at 10, 15 and 20 degrees. What you'll note though is although we got the similar amount of sporulation at 10 degrees as at the warmer temperatures, we didn't get very much symptom development. So this indicates, and we see this at the higher temperatures as well, that we get sporulation before symptom development. So this is a bit like, potentially a bit like the COVID super spreaders who don't show symptoms but are able to transmit the virus. So in these trees that we see that look green and healthy but transition to red very quickly, could this be partly explaining it, that there's infection there that isn't showing symptoms? I'm now going to talk about some of the copper trials that we've been doing at Kinleaf the last few years in close collaboration with Mike Baker of Hancock Forest Management. So in all trials, we've used the Dophystroma standard copper formulation in our trials. So in 2017, we had one application in February and an unsprayed control, and we, as I said, applied at the Dophystroma standard. And what we found in this year was that disease was significantly reduced in sprayed blocks compared to unsprayed blocks. We followed this trial up in 2018, but as well as having the February spray time, we also included other spray timings. So we had a November and a May spray timing. And what you'll see, we had it at 2 sites. You'll see on the graph on the right, we had no difference between the treatments. But on the graph on the left, you'll see the spray treatments, which are in green, had lower, significantly lower disease severity than the non-spray treatments, which are shown in red on the left. So again, copper applied at the Dophystroma standard reduced severity, but we didn't see a difference between those timings. We then followed this up in 2019, again looking at the different spray timings, so including a November, February and April spray. And what we found was that the November and February spray significantly reduced disease severity, but the April spray did not. What I must say though, in the 2018 and 2019 years, there wasn't very much disease in the trial, so we can't make any sweeping conclusions yet. Ideally, these trials would be replicated under greater disease pressure. So now I'll just talk about a few follow-up experiments where we're trying to look at growth impacts of the disease. So we've kind of extended these copper trials, again at Kinleaf, working with Mike Baker of Hancock Forest Management. And we have different spray timings. So we've got a February spray, an April spray, and we've got unsprayed blocks. And importantly, we've incorporated permanent sample plots, PSPs, into these blocks. So we can try and exclude disease using copper and then look at the impact that the disease is having. So this trial has been running since 2019 and is planned to run for at least 2 or 3 more years. So far, disease has been low in the trial, so I don't have data to present, but this year disease has been more significant, so hopefully I'll have data to show in due course. So I'll just wrap up now with some conclusions. Within the Resilient Forest Programme, we're working to develop an epidemiological model which will help us predict outbreak years and support management decisions for controlling red needlecast. Copper applied at the standard rate for Dophystroma control is effective for controlling red needlecast in the trials so far, but the disease levels haven't been significant. So ideally we would replicate these trials under higher disease levels to see if it was still remained effective. Again, we didn't see any consistent effect of spray timing, but again, we need to replicate this under greater disease pressure to be sure. Optimal spray timing may vary across regions and between years, so that's where the epidemiological model can come in and help us understand those processes and that variation. And work is underway to quantify growth impacts of the disease, which will allow a full cost-benefit analysis of control operations. So I'd just like to acknowledge Mike Baker and Hancock Forest Management and Dukin New Zealand for helping with this research, allowing access to the forests and collaborating with us. And then lots of people at Scion have been involved in the research, and there's just a list of some of them, so thanks to them as well. And thanks to you for listening, and I would be happy to take any questions.